Hey dudes, we're looking at 3-5 inverses, inverse functions that is. Try these out as a warm-up. These are composites like we were working on yesterday, and pause me until you got them. Go. Okay, so let's call this f of n, and let's call this g of n, and so we're looking for fog of 2, f of g of 2. So if you wrote that out, you'd say I want f. So here's f of, maybe I'd write it out like this, f of g of 2, right? So we're just trying to find a value, so you don't have to necessarily write all of it out, but you might have to for b. So let's just do the quick and easy method for this side. This is g of 2, so you'd put a 2 into there. So this would be into the function, into this function, 2 of something. We'd be putting in all of this with a 2 in it, so -2 minus 4. So that sounds like -6, so -12. Great. We're going to do the same thing with the g and f of x on this side. Let's call this, oh sorry, g and h, let's call that g, let's call that h. H of g of x, I always rewrite that because I think it just makes more sense to see it as g of x first, which is in purple. So this is g of x, and that goes into h, right? H of g of x, right? And then we're not evaluating, we're simply organizing them and moving on. So into h of x, here's h of x, here's h's input x, we square it, -2, and the input is all of g of x. So you could think about it like this, and if you don't want to do a second line, you just say, oh, 4x plus 1 goes in there and gets squared. Now you could leave it, but best form is to expand this. This is 16x squared plus what, 8x plus 1. And then this -2 is still hanging out at the back, -2. So it ends up as when you add the 1 and the -2 together, you get -2, or -1, sorry. Cool, great, composite functions. Inverses are sort of undoing the composite. So if it's sort of like the command Z to undo things in my mind. So this is kind of how that works. Here's an equation, y equals 2x plus 3, and you put in a 2, find the output. If you put in a 3, find the output. If you put in b, find the output. Pause me and try that. All right, if you put in 2, if you put in 5, you get 13, right? 13. If you put in 3, you get 6, you get 9. And if you put in b, you get 2b plus 3, right? So if you have a 13 and you want your 5 back, what equation do you have to put 13 in to get your 5 back? How do you get 5 back?
You want to give it back, please?
Right? How do you get that back? Well, to turn 13 into 5, you'd what? First, if you want 5, you first subtract 3. That's 10, and then divide by 2. Right? 10 divided by 2 is 5. You get your 5 back. If you want it, you have 9. You want your 3 back. You can do the same thing. Subtract 3, 6, and then divide by 2. You get your 3. Right? If you want to get your 3 back. If you want your b back, you would take this thing and you'd subtract 3, would give you 2b, and then you'd divide by 2, right? And the 2's cancel, you'd be left with b. This operation of subtracting the 3 and then dividing by 2 is the inverse operation. It's how to run backwards, right? So it's take whatever value you have, like your 13, subtract 3, 10, divide by 2. This is an inverse operation because it undoes this, runs it backwards if you want, right? So for the most part, like what we're saying with this is I want to take my inputs and turn them to outputs, and my outputs and turn them to inputs. And I'll show you kind of how to do that. So this is the same function. This is the function we were working with. This is the inverse function that undoes it. So if we put in a 1, it would double the 1, 2, and then add 3, 5. Here's the 5 that comes out. And if we run this is the output, right? If we run that output into the input of the inverse function, it undoes this original function. It subtracts 3, so 2, and then divide by 2, and 1 comes out. The original input comes out. Yeah? So we denote this backwards function as the inverse. We write it like this. The inverse of f of x. Yeah? This does not mean 1 over f of x. I know that like 2 to the negative 1 is really 1 over 2 to the first, right? This negative flips the fraction. This is a function though, it's not a number. So this, maybe you should write that down. That's not equal to 1 over f of x. This is the inverse, it means run the function backwards. Cool. Sometimes the new function, or the new relation is not a function. And sometimes they don't have an inverse. But we can always find that the equation to run it backwards. I'll give you some examples. So this part comes up a lot, that the domain of the inverse is equal to the range of the original function. And the range of the inverse is equal to the domain of the original function. So write that down and I'll give you an example of it. This is saying the x's of the inverse are the y's of the original, and the y's of the inverse are the x's of the original. That makes sense because here, this is an x, it's an input. The output's a 5 for this original function. But in the inverse function, the 5 is the x, right? The 5 was the y for this one. The 5 is the x for this one because it's going in. And lo and behold, out comes the 1 as the y for the inverse. But it was the x, it was the input originally. So the x's and y's switch, right? You can see that if you graph a function and its inverse. Here's this orange function is this line. Blow that up a little bit. The orange one is this line. Oh, wrong one. And the green is the original, and the green is the inverse. And if you look at these, this point is here, I don't know, making that up, 3, 0. And this point is 0, 3 on the original. Same with this. This is 1, 2, I don't know, let's call this -1. 0, comma, -1. And this point here, its corresponding point is -1, comma, 0. Right? So you can see that they've switched the x for y and the y for x for both of these. That's a 3. Right? We've switched the x's and y's. Same thing here. The domain becomes the range, the x's become the y's become the x's. So, for example, here's root x plus 3. The domain of this is going to be, let's see, well, it's the radicand, the stuff inside, can't be negative. It can be 0, but it can't be negative. So it's got to be greater than or equal to 0. Yeah. So if you solve that, it's got to be x has to be greater than or equal to -3. You can get a 0, that's fine. Therefore, if that's true, the outputs, if -3 is the smallest thing you can put in, then 0 is the smallest thing in here that you'll get, and square root of 0 is 0, and you'll get only things bigger than that. So the y's are going to be greater than or equal to 0. Therefore, this is not a new function. This is inextricably tied, since it's the inverse. It's inextricably tied to that function. They're like evil twins, right? And therefore, you can't assess this function's domain and range independently. It's tied to this one. And so, which kind of makes it easier because you can just take this and say, oh, this was the domain, now it's the range, this was the range, now it's the domain, except you switch x and y. Yeah, that's what inverses do. They switch x and y. There's an easy way to figure these out, and that's just physically switch the x and y. If you work, let's go back to this guy. If you didn't know that this was the inverse, you'd find the inverse by taking this guy, y equals 2x plus 3. You'd switch the x and y's around. You'd say, oh, I want my x's to become y's, my y's to become x's. And then you solve for that y. Right, you subtract 3, you get this moved out of the way, that's for sure. You get x minus 3 equals 2y. And then you divide by 2, you get y equals this, right? Just what we had before, x minus 3 over 2. Same thing here. These are inverses. I just told you and you took it on blind faith. But if you started with this, if you said this is y equals root x plus 3, if you want to find the inverse, you switch x's and y's. I want my y's to become x's, my x's to become y's. That's what an inverse does. And then you'd solve for that y by squaring both sides. The square and the radical cancel out. You get x squared is y plus 3. So you'd subtract a 3 and you'd get x squared minus 3, just like we expected. Yeah? But this is not an independent function again. It's inextricably tied to that one. And so the x's become the y values and the y's become the x values. That's what an inverse does, right? Okay. So you can also like make composites of these inverse functions, which is kind of interesting and helps clarify what we're seeing. So here's f of x, here's inverse of f of x. And I want to compose them. So this I want to make f of its inverse. So you'd say f of is 2 times the input plus 3, and the input is inverse of f of x. So you go like that, plug that in there. When you simplify this, the 2 times all this mess divided by 2, those cancel out, and you get x minus 3 plus 3 is just x. Right? The function and its inverse have essentially canceled out and you're just left with that input, which makes sense if you're thinking about this as a composition of functions. If we first put in an input and we run the f function and then we run the inverse of it, you should get the exact same output out. So that makes sense. Ka-ching. And also, if you do the same thing but with inverse of f first, so you'd start with the input minus 3, right? The x minus 3 all over 2, and the input is f of x, so the input is 2x plus 3. Simplify. This is 2x plus 3 minus 3, those cancel out. This is 2x divided by 2, those cancel out. You're left with x. It doesn't matter which way you compose them, you always get this inverse that undoes the function, right? Great, so that's kind of what we're seeing. All right, so this is, let's see, this is the fact that inverse of f is not the reciprocal. It's not 1 over f of x. It's the inverse, just to be clear. So here's f of x, here's a different f of x. Quickly see if you can find me the inverses of those two. And then we'll look at another problem with the inverse. Okay, so this, the inverse of f of x, we could call this y equals 5x plus 2. If we wanted to find the inverse, we'd switch x's and y's. That's what I want my inverse to do, is give me y's back when I have, or x's back when I've found my y's. Subtract 2 from both sides, divide by 5, and you get the new y value, or the inverse function. So you'd say, okay, oh, and now my inverse of f is x minus 2 over 5. Great, so that's there's my f of x, and there's my inverse of f of x. You can see that this, if you graph this, it looks like this one. And you can see that they're reflected over the xy axis. This point is the x equals y axis, which means 1, 1 is on there, 2, 2 is on there, 3, 3 is on there, 4, 4 is on there, right? And we're switching our x's and y's, so it's flipping over this xy axis. And that's how you can sometimes visually see inverses without doing too much work. Just check if they're inverses graphically. Inverse of this would be the inverse of f of x is just what, root x. And if you graphed one, this is the root function. This is the other function, and you can see that they're flipped. This point is flipped over the xy. This point is flipped over the xy. So visually, they look like they are good candidates that are inverses. Cool. Once in a while, you get a problem where the inverse is not a function. This is a function because it passes the vertical line test, and so does this one. So the function and its inverse are both actually functions. That's great. Thumbs up. This is the same. Let's see. Let's clear this up a little bit. With the red function passes the vertical line test. It's a function. The black line passes the vertical line test. It's a function, and that's great. But the problem with this, if you took all of f of x and you took all of the inverse, which is the root of x, sometimes its inverse is not a full function, right? One x value gives you 2 y value outputs. It doesn't mean it's bad or wrong, it just means it doesn't behave like a function, yeah? Which means that one input gives you 2 outputs. Interesting? Okay. So what I'd like you to try is work through, there's 2 inverse function sections in your packet. Try those out, and I'll see you later.